Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series. Now, in just a minute, I'll be thrilled to roll out this week's seminar with Benjamin Bichsel. I'm so glad that some of you have joined us early today on time. And before we begin with introductions, we'd love to give everyone just about a minute or two to tune into the live stream. Meanwhile, you can practice asking questions and replying to each other's comments. We like to keep this very lively and community focused. My favorite question, of course, as some of you already know, is where's everyone tuning in from today? You can reply to that in the comment chat box here on YouTube, which is located above, right, left, or below, somewhere on your screen. And that's the same place where you can ask Benjamin and myself questions during the talk. We like to keep this lively and interactive. So you can always go back, subscribe, know what's coming up, and watch the recording. But the live discussion part only comes now. And today I see we have folks from Texas, Washington, New York, Virginia, St. Paul, India. So glad to see everybody making all the different time zones. As you know, you can always catch up on things. But folks, it's only now at noon Eastern time that we can get into the live action part of this. So with that, I think it's time that we begin. I'm thrilled to roll out the latest episode of the IBM Qiskit Live Quantum Seminar Series dedicated to you, the research and academic communities. I'm your host, Zlatko Minev from IBM Quantum Research. And today I have the special pleasure and privilege of hosting Benjamin Bichsel from Martin Vetchev's group at ETH Zürich. I had the pleasure to visit you guys not so long ago and have a nice chat. Benjamin will speak on high-level quantum programming with the Silq framework, which we'll see maybe looks very close to classical programming for quantum computers. Benjamin, before we hand over the stage to you, I'd like to give a little bit of a bio. Benjamin is a PhD student at ETH Zürich, supervised by Martin Vetchev. Benjamin has led the development of Silq, which is part of a broader effort to bridge the gap between classical and quantum languages and to lower the entrance barrier for non-expert quantum programmers. How are you today, Benjamin?
I'm great. Thank you.
Awesome. Well, we're really glad to see you. I see the chat is very active, and you've got folks from Switzerland, Taiwan, France, Netherlands, Chicago, New York, so many time zones. I'd like to turn it over to you. The stage is yours.
Great. So thanks a lot for this very nice introduction, and welcome everyone to this talk on Silq, a high-level quantum programming language. My name is Benjamin, and I developed Silq together with Maximilian, Timon, and Martin Vetchev, and we are all from ETH Zürich, as Zlatko said. So to give you a bit of context for this talk, the list of quantum languages is growing constantly. Here I show you a few examples. I would imagine that you know Qiskit if you're attending this talk. You may have already seen other quantum languages around, like Q# or Silq, maybe Quipper, Project Q, or Liquid. So a valid question is, what makes Silq so different? And the answer is that in contrast to other quantum languages, Silq supports a descriptive view on quantum algorithms that expresses the high-level intent of the programmer. And as a consequence, Silq programs are typically shorter and simpler, and they prevent a lot of errors already before you even run the program. And they modify the program's quantum state according to an intuitive semantics that follows the laws of quantum physics. So the outline for the talk today is that we will start off with the standard part of Silq, which exists analogously also in other languages, such as Qiskit. Then we will move on to the advanced features of Silq, which are both novel and unique to Silq. And finally, I will quickly broaden the view and discuss how programming language techniques more generally can help with quantum computing. So to showcase Silq, we will use this running example. So here the task is that you're given a function that takes a Boolean and returns a Boolean. And you would like to know if this function is constant or balanced. So if it always returns the same output, no matter if the input is 0 or 1, or if it returns a different output depending on the input. And here I show you a trivial classical solution to this, which is already written in Silq, so we get a chance to get a head start on Silq's syntax. So what's happening here is that I have defined this trivial function, which takes as an argument this f function. And this f function takes itself as an argument a Boolean, which is annotated with this exclamation mark. And the exclamation mark indicates that the Boolean is classical. And finally, this arrow indicates that f is a function. So overall, what we get is that this trivial solution gets a function, f, that takes a classical Boolean and returns a classical Boolean. And we would like to know if this function is constant or balanced. And in order to do this, what we can do is we can evaluate f on false or 0. We get some output 0. And we can evaluate f on true or 1, and we get some output. Then we can just check if the two outputs are the same, right? So this is just, you could do this in any classical language. But we would like to know how we can solve this with quantum language, or more generally more precisely with Silq. However, before we can do this, so what I forgot to mention before is that this column exclamation mark means that we're writing to a fresh variable. So what's happening here is we evaluate f on false, and because this is the first time we write to this variable output 0, we write colon equals. If you would overwrite this variable later on, then we would write just a standard equal sign.
Right. Quick question, maybe we'll get to this, but will the inputs be constrained to be classical, or could they themselves be quantum registers?
Right, so in this case, the input itself is a function which is classical, as is annotated by this exclamation mark before the function. Silq also supports quantum functions which don't have this exclamation mark, but for the purpose of this talk, we can assume that all functions are classically known. So you can assume that this arrow is always preceded by the exclamation mark. And the function operates on classical inputs and produces classical outputs. And we will see later on that if you omit this exclamation mark, then you will operate on a quantum Boolean, for example. And yeah, so in general, thanks a lot for the question. And of course, if you have questions on the chat, feel free to ask them, and Zlatko will forward them to me. I'm very happy to clarify questions early on, as opposed to later when everything may then get exacerbated by further details. So, okay, so this is just a classical solution to this task of figuring out if the function is constant or balanced. And before we can look at the quantum solution to this task, let me provide you a very quick background in quantum computation, which focuses on the more advanced concepts needed in this talk. I assume you already know about quantum states and measurement and this type of stuff. But some of the more advanced concepts, I think it helps to revise them quickly before we get into the details here. So the first concept is the principle of deferred measurement. You may have seen this already. So what this means is that if we have some quantum circuit, and this quantum circuit applies a measurement on some qubit, then this is equivalent to just applying this measurement at the very end of the circuit. So these two circuits would be equivalent in the sense that the output distributions of these three measurements would be the same in both cases. Now, I mean, this is well known, so why is it relevant in the context of our talk? And the reason is that a common occurrence in quantum computation is that we have some circuit, and we have some qubit that we need in part of the computation here. But actually, we don't really care about the result, right? So we measure these other two qubits, and we leverage the results for some classical post-processing or something. And this temporary qubit, we used it earlier on in the computation, and now we don't care. So maybe we leave it lying around, and just after the computation has finished, we discard it. So clearly, if I apply a measurement to this, after everything else in my computation is already finished, this won't affect the result of the previous measurements. So applying a measurement at the very end will not affect the old measurements that I actually cared about. But now, interestingly, the principle of deferred measurement says that this is equivalent to applying the measurement immediately. And this may be surprising, because what this means is that if I have a qubit and I know that down the line I will not care about it, then I should assume that it's measured immediately. And this can also be dangerous because, as you probably know, if I measure a qubit, then it will collapse. And if it's entangled with other qubits, then it can even collapse these qubits, which means that if I have some temporary qubit that I don't care about, just the fact that I don't care about this qubit may induce an implicit measurement on qubits that I do care about. So this is quite unintuitive, especially for classical programmers. And we will see how this is an issue then if you want to actually write programs, and how Silq gets around this issue. So again, I mean, if there are any questions on this, happy to answer them, but I'll just move on and assume that Zlatko lets me know if there are any pressing questions. The second concept we will need is that of the no cloning theorem. So in classical computation, what you can do is here you just have this function. It takes a classical Boolean and it returns 2 copies of this Boolean. And this is totally fine in classical programming. So the semantics of this would be if the input Boolean is B, so for example 0, then it would just produce 2 copies of this B0. In quantum, things are quite a bit more hairy. So here we see an example that tries to clone a qubit. So here, as I announced previously, we see that X is now annotated just as B, so as a qubit quantum Boolean. And we try to return 2 copies of B. So the most reasonable interpretation about the semantics of this would be to say, well, if the state is psi, then we just return 2 copies of psi. So for example, if the input state would be plus, then we just return 2 copies of the plus state. Now, unfortunately, this is unphysical, so it's not even linear, which means that you can never realize this mapping. And this is also why in Silq we don't actually allow this program. And we will see this later also in the live demo, where if you try to access variables that are already used in some other place, then Silq will complain statically. What can sometimes lead to confusion, though, is that something is possible, and we call this duplication. So what I'm doing here is I have a simple program that takes the variable or qubit X, and it first duplicates this qubit, gets the result Y, and then it returns both this duplicate Y and the original X. And the intended semantics of this is that it just operates on the computational basis state. So if we start with cat 0, for example, we would return cat 0 and cat 0, the 2 copies. And if we start on a superposition, we would just linearly extend it to this superposition. So for example, if we start on the plus state as before, let's see state cat 0 plus cat 1, then we would just get state cat 0 tensor cat 0 plus cat 1 tensor cat 1. And so just to note here, I'm a bit lazy here and I'm omitting the normalization. This is just to simplify the notational clutter a bit. So typically you would have a 1 over square root of 2 prefactor here, but I omit this throughout this presentation. So
And
this no cloning, yes, go ahead.
just remind us the notation. So colon mathBBB means that it's a classical binary string. Is that the notation? Or quantum bit?
Where you mean here?
Yes.
Yeah, so this means that X is a qubit, whereas the exclamation mark means that X would be a classical bit. So this program you could essentially also write in any other languages, right? For example, in Python, you could write this. Whereas this one you can't really write, or at least the intended use you can't write, because the idea is that this is a qubit, so you would need some quantum framework to express this, for example, Qiskit. Does this make sense?
Yes, I think so. Thanks.
Okay, right. And then the last concept we will need is that of a quantum oracle, which allows us to run a classical function f on a quantum computer. So ideally, we would want to realize this functionality. So we start with a state that if we start with a state that's in cat x, then we just want to produce cat f of x. Now, unfortunately, this is not possible because quantum computation only supports reversible operations. So for example, if f would be constant or f constantly 0, then this would always be cat 0, which means that from the output we cannot infer what the input was. And therefore, we can never hope to realize this, or at least not in general, we cannot realize this functionality on a quantum computer. And the typical way to get around this is to introduce the quantum oracle for f, which produces f of x, but it also preserves x. So the idea is that we feed in cat x and also some scratch variable, cat y, and we preserve cat x. And on the scratch variable, we return y, x, or f of x, with the idea that we will initialize y as 0. So if this is 0, then 0, x, or f of x is f of x. So this is just f of x. So we can show this here explicitly. So if x is 0 and y is 0, then x is preserved to be 0 and y gets f of 0. And if x is 1, then again, x is preserved and y gets f of 1. And this is, of course, also well defined in the case where y is 1. But we don't really care about this because typically we don't feed in another state other than 0 here. And as usual, this quantum oracle is linear. So we get the expected behavior on superpositions here. Right. Okay. So with this, we are ready to show how we can solve the problem I introduced before using the Deutsch-Jozsa algorithm, a well-known quantum algorithm that addresses exactly this problem. So we're given the quantum oracle and we're determining if the underlying function is constant or balanced. And we do this with just a single invocation to the quantum oracle. So classically before, we needed 2 invocations. We needed to evaluate f of 0 and f of 1, and then compare the two. And now we can just evaluate the quantum oracle only once. And the way we do this is like this. So I will go briefly over this. Again, I assume you've probably seen this around, but some of the details here will be helpful to understand the Silq code later on. So I will go over this. So we initialize 2 qubits with cat 0 and cat 1 respectively. Then we apply the Hadamard to both qubits, which moves us to state cat plus and cat minus. Then we apply the quantum oracle to this, and we get to this nasty looking state with some back of the envelope calculation. You can actually confirm that this is the right result. And now what's interesting is that the second qubit is in state cat minus, which means that it's unentangled with the rest of the state, which means that if we ignore it, even though it gets measured, as I discussed before, this measurement doesn't have a side effect on this wire up here. So we can just drop this part of the states, and we are left with this state here, which is essentially just a superposition of cat 0 and cat 1, but the prefactors, -1 or +1, depend on f of x. If we feed this through a final Hadamard, then we get cat 0 or cat 1, depending on whether the function is constant or balanced. So if we measure this, then we get exactly in a classical sense 0 or 1, depending on whether the function is constant or balanced. And because this state will be relevant later on, let me quickly show you how we can confirm that this actually maps to the right cat 0 or cat 1. So what we want to see is why this state, if we push it through a Hadamard, gets to cat 0 or cat 1, depending on if the function is constant or balanced. And we can check this just by a case distinction. So for example, in this entry here, we check what happens if f of 0 is 0 and f of 1 is 0. In this case, this is always 0 up here. So this is always 1. So we are just left with cat 0 plus cat 1, which is the plus state. So if we push this through the Hadamard, we just get cat 0, which is exactly what we expect, because here the function is constant. It always returns 0. And in this case, we expect cat 0, and we indeed get cat 0. And we can check a similar thing for all the other cases, and we will see that everything works out, assuming we ignore some global phase down here. Right, so with this, I hope that you're all on board and you remembered what the Deutsch-Jozsa algorithm is. So let's see how we can implement this in Silq. And the way we can do this is here I have some implementation of Deutsch-Jozsa. And again, it takes an argument, but this time the argument is a quantum oracle. And the type of this quantum oracle is that it takes 2 qubits and it returns 2 qubits. And if we can compare this to previously what the input was to the classical solution, then we will see that there are some differences, right? So now we are taking 2 qubits and returning 2 qubits. Before we took 1 classical bit and returned 1 classical bit. So as I said, this quantum oracle is kind of important to even be able to run this on a quantum computer. So at first, we just do the same thing, and then later on, we will use the quantum oracle. So at first, we initialize x to be 0 and y to be 1, where this :b means that we interpret 0 as the quantum bit, ket 0, and analogously for 1 being assigned to, for y being assigned to 1. And then we apply the Hadamard to both x and y. So down here, you can see what happens in terms of the circuit. So we feed 0 and 1 into their respective Hadamards. And what's important to note here is that this is already a bit different than what you would see in other quantum languages. So the idea is that in general, you can write a Hadamard like this. So you have some qubit x, you feed it into the Hadamard, and then you get to assign a new name to the output. And the way you can interpret this, if you're more familiar with quantum circuits, is that the input wire was named X. You feed this wire into the Hadamard, and then the output wire is named Y now. And because often you don't actually want to rename the wire, this pattern exists quite frequently in Silq. So you feed X into the Hadamard, and you call the output X again. So this would correspond to this pattern here. And what's important to note here is that the Hadamard actually consumes its argument. So if you would try to write something like this in Silq, then we would get an error. So what we're trying to do here is we're trying to feed the X into the Hadamard, and we're calling the output Y. Then we're trying to feed X again into the Hadamard, but X is already gone, right? It was consumed up here when we fed it into the Hadamard. And in terms of circuits, this would mean this would look somehow like this, where we try to feed the same wire into two Hadamards, which is not possible, in part due to the no cloning theorem that I mentioned earlier, right? Because in order to feed the same value into two operations, we would need to clone it. This is not physical, so Silq doesn't allow this. Of course, if you want to just apply the Hadamard twice to the same wire, then you can do this. So you could just feed X into the Hadamard, call the output X again, and then feed this X into the Hadamard again and call the output X again. So this is a straightforward pattern that you could use. But up here, if you're trying to refer to outdated variables, then this will be disallowed in Silq. Right, so just to restate what we had, we initialized X and Y to 0 and 1 respectively. We applied the Hadamard to both. Now we're feeding X and Y into this quantum oracle here. So in here, we're feeding both wires into the quantum oracle, and we're calling the outputs X and Y again. And now one specialty of Silq is that after this, remember I told you that this value is unentangled, so it gets measured if we discard it, but this measurement doesn't have an effect. Now, in general, this is not the case, right? This measurement could have an effect, and Silq forces us to make this measurement explicit because we don't want hidden side effects in Silq. We want every effect to be explicit. So as a programmer, you have to state explicitly that you're measuring Y. But of course, if you understand Deutsch-Jozsa, then you will know that this measurement has no effect. Now we can also apply the Hadamard. So we feed in the X wire, we get the X wire back, and we return the measurement of X, and we're done. So this showcases sort of the simple part of Silq, but it doesn't really exploit any of the interesting features of Silq. So for the next part of my talk, I would like to show an idiomatic implementation in Silq. So I want to show what the most intuitive way is to prepare this key state that we have seen before. So remember, in this state, we have some superposition of ket 0 and ket 1, and the prefactors encode sort of this function f. But in order to actually use the features of Silq, we have to, of course, first introduce them. So I will do that first. So the first feature of Silq is something that's maybe not so surprising, which is the quantum conditional, which, for example, says if X, then apply the Hadamard to Y. So if you look at this in terms of states, then the first qubit is X and the second qubit is Y. So if X is 0, then nothing happens. So we should expect that Y doesn't get affected in this case. But if X is 1, then we want to apply the Hadamard. So we preserve X, but we apply the Hadamard to Y. So this ket 1 gets mapped to ket minus. And if you prefer to think in terms of circuits, then this is probably also not so surprising. This just corresponds to the controlled Hadamard application on X and Y. Now things get more interesting.
Before I let you get a little too far, and maybe we'll cover this soon. You mentioned how, for instance, Silq won't let you not measure Y or not or try to use X in two different Hadamard outputs. What does that mean operationally? Is there a linter or a compiler? How does that look?
Great question. We will see this in action later on, but the quick answer is that Silq has a type system which is linear. I guess. I mean, this is more of a terminology from the programming language community, but a linear type system enforces that every variable can be used exactly once. So you always know where your variable is, sort of, and you can actually detect if it's not being measured. But we will see this also in action. I think in the live demo, this is a bit more intuitive because we will see explicitly where Silq tells you, oh, actually, you have a problem here. Does this answer your question for now?
I think it gives me enough of a good direction. Yes.
If I don't answer it during the talk, feel free to follow up in the end, or maybe in the live demo, we can see it there also.
Okay.
Right, so getting back to this example here, before we saw the quantum conditional that just corresponds to a controlled application. So this is kind of standard stuff, although it wasn't, like this generality wasn't in Qiskit for a long time, but in the meantime, it's there now if I followed Qiskit correctly. Things get more interesting if you move on to this example. Here we want to say, if X then apply phase of pi, and phase of pi swaps the sign. So what we should expect here is that if we are in this superposition of ket 0 and ket 1, if X is 0, then we don't do anything, right? So 0 gets preserved. If X is 1, then we want to swap the sign. So we swap the sign from plus to minus. And already we can see now that things get a bit more difficult if you think about circuits, because now we cannot compile this down to a controlled application. Instead, like the most natural way to compile this would be just in terms of a set gate. And what we can see here is sort of a general pattern of Silq, which says that our design philosophy for Silq was to think about how Silq evolves states. And it's not so much about how it can be compiled down to circuits. If you compare almost all existing quantum languages, their goal is to just describe this circuit. In Silq, we want to describe how we act on quantum states. And compilation is then a second order concern. So this, I think, is already interesting, but things get a lot more interesting even if we talk about temporary values. I already hinted at this before in the very beginning when I talked about how temporary values get measured immediately. And now we will see this in action. So here we have a very simple Silq program that computes the OR of A, B, C and stores it into D. So let's see what the expected outcome is on a very simple state where A is 0, B is 1, and C is 0. I would assume that everyone who attends here today would think that the output is quite straightforward. We just compute the OR of A, B, C, and the OR is 1 because B is 1. So what we should expect to happen here is to just have this additional qubit that holds 1. Now, if we want to compile this down to a circuit, things are actually not as easy as they seem in Silq. So let's try to compile this to a circuit. So here we have 3 wires, A, B, and C, and they are initialized with the same state as before. So A is 0, B is 1, C is 0. So we cannot implement this directly. So let's first compute the OR of AB. Let's assume we have a quantum oracle for this already. So we allocate a new qubit, we initialize it with ket 0, and the quantum oracle will compute the OR of AB. So in terms of our example state, this new qubit will hold 1, again, because B is 1. Now, next step, we can use this temporary value, the OR of AB, to compute our final result, right? So we add another quantum oracle that computes the OR of the OR of AB together with C. So if we allocate another qubit, initialize it with 0, then ultimately we get A or B or C on this wire. However, there's a problem, because down here, even though we have computed the OR of ABC correctly, we still have the OR of AB lying around. And that's problematic because, as I discussed in the very beginning, we should assume that this gets measured, even if we just keep it around until the very end of the computation. Semantically, we should assume that this gets measured immediately. And therefore, if we measure it, in this concrete example, it's not an issue, but in general, if we start from a superposition, then this will be a superposition, and therefore we will collapse the state in this case, and we will sort of screw up the computation. So the standard way to fix this is to introduce so-called uncomputation. So we can introduce this adjoint or inverse gate of the OR quantum oracle, which will reset the OR of AB back to 0. And after this, we can safely discard it because it's no longer entangled with the remainder of the state. So we can drop it and we get exactly what we want. So that's all nice and good. But in order to do this, we actually have to synthesize this uncomputation, right? Because it's not in the original Silq code. So let's see a bit under the hood, and let's see how Silq handles this. So you could imagine that behind the scenes, if you write this OR of ABC, what Silq does is it also allocates a temporary variable that stores the OR of AB. Then it uses this temporary variable to compute and ORs it with C to compute D. And then it forgets the temporary variable. So let's see what happens here semantically. So initially we have ABC. Then we initialize an additional qubit that stores the OR of AB. Then we compute the final result, the OR of ABC. And now the crucial steps comes, and we want to forget this temporary variable here. So what Silq does is it just drops this from the state. But in order to do this, as we have seen before, you need to introduce some uncomputation behind the scenes. And whether this is even physically possible is not always clear. So Silq checks two side conditions. So these are conditions under which this uncomputation step is safe. And if this condition is met, then Silq will allow us to just silently drop this temporary variable. So here we don't even have it. And if you would program in Silq, you wouldn't even need to write this forget. It would just forget it implicitly. And if these conditions are not met, then Silq will complain and say that it doesn't know how to uncompute the temporary variable. And the two conditions are, first, that the temporary value was computed via a Q-free function, where Q-free sort of means that it's free of quantum interaction. So for example, this OR, if we would say that it's Q-free because we can describe it classically, right? The OR, it's just, if you give it computational basis states, it will produce computational basis states again. So essentially the OR is a classical operation. In contrast, the Hadamard operation is not really classical because, for example, it moves cat 0 to cat plus. So we would say that OR is Q-free, whereas Hadamard is not. So the first condition is that the OR is that the temporary value was computed by a Q-free function, and the second condition is that the temporary value depends on values which were preserved. So in this case, this OR depends on A and B, and both are still around here, so they are actually available for uncomputation. And if these two conditions are met, then Silq could say, okay, great, uncomputation can be done behind the scenes. I can handle this for you. And it would just allow you to drop this temporary variable. And let's just take a quick look. Right. So how do we actually know? I think Zlatko hinted at this before a bit. How do we know that just looking at the program, whether this temporary variable was computed by a Q-free function and whether the values were preserved? And this is done via Silq's type system. So here I show my own implementation of OR. We also have this as a built-in feature, but just to make it clear what's happening here. This my OR function returns the OR of AB using the De Morgan rules. The implementation details are not so important. What's important is how the types of this function are annotated. So first, we say that A is const, which means that my OR actually preserves A. So if we call my OR, then A will still be around at the end of the call. And in a similar sense, Q3 indicates that the function can be described classically, so that it doesn't actually induce any fresh superposition. It's essentially a classical function. And because this combination of constant Q3 is so common, Silq induces this syntactic sugar lifted for it. So if you see a function annotated as lifted, then you can know that this is just syntactic sugar for constant Q3. So the function would be Q3 and its two arguments would be const. And if you see such a function and you use it, for example, here, you call my/or for a, b, then you know semantically that a and b are preserved because they're const. And you know that the new variable can be computed using a Q3 function. And this in turn means that down the line, even much later, assuming that a and b are still around, you will be able to uncompute this temporary variable. So that's how Silq behind the scenes ensures that you can't prevent correct uncomputation. So let's just see how other quantum languages handle this. So in Silq, as I just showed you before, you can just compute the OR of ABC, no problem. In other languages, this is quite a bit nastier. So for example, in Q#, you would have to allocate a fresh qubit, then store the OR of AB into this temporary qubit, then store the OR of TC into D, and then don't forget to do the uncomputation and explicitly do this inverse OR gate. Because some people have noticed that this pattern is quite inconvenient, some languages have introduced convenience features such as with computed. So here this snippet means that first compute the OR of AB, call the result T, and OR T with C, this is the final result. And then because we used with computed, remember to again uncompute this temporary variable here. But I would argue still that overall this looks a lot nicer and is more interpretable than this here. And probably more crucially, here we don't really check the safety conditions that I discussed before. So we could use this also with non-Q3 functions or with A that gets modified in the meantime somewhere, which means that it's actually not clear if this with computed really resets T correctly to 0. So Silq is both simpler, more intuitive, and it's also safer in this case. And if you're only familiar with Qiskit, then you should expect a pattern that's a bit similar to here. So in Qiskit, you shouldn't forget this uncomputation, otherwise you will get this implicit measurement.
What happens if I forget to put the lifted in my def of my OR? Let's say I have a developer error.
Right, so then you would, I mean, in this case, if you actually forget the lifted, you would have multiple issues immediately. So even if you're writing the code, you would get an error. I think actually the Q3 would even be inferred automatically because like we can do this statically, but let's assume it's not. Then like the Q3 you would forget, and therefore if you try to use my OR down here, it would not know that it's Q3, and therefore it will not allow you to drop this C later on. But you would also get an error here because Silq would realize that, well, A and B, they are used, but they're not actually consumed, so they're still around after you call my OR, yet you didn't annotate them as const. So Silq would already complain just if you're coding the my OR, and we will also see this in the live demo.
I see.
So the high-level takeaway is that if you make a mistake, then chances are that Silq will notify you of this mistake even before you run any code at all, just through its type system.
I see. And where the output is routed to, you don't yet know based on this function, because you could route it back to A or B, presumably, and not something else. You could try to do something like that.
Yes, but still, I mean, here we produce a new return value. So if you would reroute this into A, things would still be super confusing because you would then overwrite the old variable of A, and that's sort of a reset, which in itself is sort of a measurement. So I mean, here I think really the fix would be to annotate these as const at the very least. Otherwise, you don't really. Yeah. Otherwise, it's confusing. But we will also see this in the live demo.
Thanks.
Any other questions?
Yeah, folks, feel free to repost. There was quite a bit of chat here, so if I missed your question, feel free to repost it, and I'll get it back up to you, Benjamin.
Okay, great. In the meantime, I will just continue. So I showed that uncomputation in other languages is not so great. Silq is safer. And with this now, let's see how we can do an idiomatic implementation of Deutsch-Jozsa. This is what I promised in the beginning, and now let me actually deliver on that promise. So now Deutsch-Jozsa takes a lifted function that takes a qubit and returns a qubit. And because it's lifted, it actually preserves the initial qubit. Then it initializes qubit x with 0. So we are in ket 0 state here. Then it applies the Hadamard. So we are in state ket plus, which is just a sum of ket 0 and ket 1. Now it says if f of x. So let's evaluate f of x. And because f is lifted, we know that x is preserved. And this second qubit, f of x, can be described using a Q3, or if you want a classical function. And if f of x, then we want to switch the sign with phase of pi. So we can write this as this, and let me demonstrate that this is exactly what you want. So if f of x is 0, then this will be 1. So the prefactor is 1, so it doesn't actually change anything. If f of x is 1, then this is -1. So we exactly swap the sign if f of x is true. So that's already a great sign. And if we exit the conditional, then we implicitly and automatically uncompute f of x, which we can do because f is lifted. And now we're already at this crucial state that I have highlighted before, the superposition of ket 0 and ket 1. So if you apply the Hadamard as I showed before, then we get exactly ket 0 or ket 1, depending on whether the function is constant or balanced. Okay. I sense a question.
No, thank you. Go on. It's taking a note.
Okay. Okay. So just for the sake of completeness, let me note that Deutsch-Jozsa is often not presented in this simple way, where the function just has a single qubit as an input, but you can also describe it if it has n qubits as input. And here I show that this is also possible in Silq. So we can parameterize Deutsch-Jozsa by saying how many qubits it takes as an input. And here, just for convenience, we interpret this input as an unsigned integer. So we say that these n qubits, we can interpret them as an n qubit unsigned integer. We could also do something else here, but this is probably the simplest in Silq. Then we initialize x with 0, but this time this 0 represents a whole unsigned integer consisting of n qubits. Then we apply the Hadamard to every qubit in this unsigned integer with a for loop. Then exactly as before, if f of x, then we switch the sign. Now we apply the Hadamard to every qubit again. And finally, we measure x, which again now gives us an unsigned integer. And if this unsigned integer is 0, then we say that the function was, I think, constant. And otherwise, we say it was balanced. So this is just to demonstrate that Silq can handle these cases where you have a parameterized number of arguments for f.
Yeah, quick question from the audience. But can you say more about what the data types mean here for qubits? So there's like integers, floats, and so on, and classical data types. And
Right. Good question. So we don't have floats because floats are quite nasty in quantum computation, like addition, for example. It's not so clear if it's even reversible. So we focus on integers and unsigned integers. Also a few other data types like vectors or tuples. If you want to, you can take a look at our webpage where all of this is listed. But here, what's happening is that we say that this f takes just n qubits. You can see this from the n, but we interpret these n qubits as a single unsigned integer. So this is analogous. If you're in the classical world, you would say, well, we have n bits, but together these n bits represent a single unsigned integer. And now we just have a quantum unsigned integer, which consists of n qubits. I'm not sure if this helped. Let's hope
Yeah,
so.
I think so. And the uncomputation is also realized at the hardware level, and it will cause an increase in the depth of the circuit usually, right?
Yes, yeah, that's a great question. So, but for this, I should say that Silq currently is mostly the language. So we have focused on creating a nice interface in which you can describe quantum algorithms. We also know that all of this can be compiled to a circuit. As I said, it's critical, of course, that Silq programs are physical. Otherwise, what are you doing? Like if you're describing programs that you will not be able to realize on a quantum computer, then it's a bit weird. But we haven't implemented a compiler for Silq yet. But we do, I mean, of course, like if you create a compiler, then you will automatically generate gates, automatically generate gates that do the uncomputation. And we have some preliminary results that show that this is both feasible and it's actually more efficient than if you would do it manually. If I have time in the end, I can say a few sentences about this.
Yeah, thanks. Yeah, we can maybe get to that also at the end.
Okay, great. Right, so let me move on to the live demo of Silq's type system, where I can show how Silq prevents errors and also how it enables uncomputation. So I will switch over to the VS Code. You should see a mostly black screen now. If not, please complain. And what we have started here is VS Code together with Silq's extension. So it's very easy to download. If you would want to try it out, I will show the link after this live demo. And so here we just have the, essentially we're doing the Silq's type checking, and Silq will tell us immediately if something is wrong. So let's go over a few issues that you could program incorrectly, and let's see how Silq flags them and sometimes how you can fix them. So here I have a function, and this function tries to reverse a measurement. And why does it do that? I mean, it tries to return the reverse of measure, where measure is the measurement function. And Silq immediately complains and tells us that the reversed function must be M-free. So it must be free of measurement, and clearly measure is a measurement, so it's not free of measurement. So Silq tells us that you can't reverse or undo essentially a measurement, which kind of makes sense. And if you would try the same thing, for example, in Qiskit, then you would also get an error, but much later on. Right? So here we get this error before we even run anything, because the type system tells us that something is wrong. In Qiskit, you would have to run your Python program, and then you would get some runtime error. So that's the difference there. And what's quite nice is that this also works if we tried to hide the measurement inside a function. So here I have this function that just tries to reverse a generic function f. Right? So this is a function that takes a qubit and returns a qubit. And I want to return the reverse of the function f. And again, Silq complains and says that the reversed function must be M-free. And this makes sense because this function, which we pass here, could actually hide a measurement. So I demonstrate this down here. So let's say we have some function that hides a measurement. So it takes a qubit q, it measures this qubit, and then it just returns a fresh qubit 0. And of course, if we would accept this function here, then we could just call this reverse f with the function hiding a measurement, and now we could sort of inadvertently reverse a measurement, which is unphysical. And because this would be possible, Silq flags this immediately here. And in order to fix this, we need to promise that we will definitely never provide a function that contains a measurement here. So we can annotate this function as M-free. And now this is fine, but down here, we get an error because now the function that hides a measurement, we know that it's not M-free. Reverse of f requires an M-free function. There's some display error here. But so this will not be accepted because the hide measurement function is not Q-free. So this is an example of if you try to reverse a measurement but sort of obfuscate your attempt, then Silq will still catch this. And a similar issue revolving around measurements is if you... Yeah?
Oh, yeah. Two quick questions before we go too far. Simple one. How do you type the BBB?
Oh, that's a common question. Sorry, I forgot to mention this. So the first answer is that if you really can't figure out how to do it, then you can just use the standard B and everything will still work out. And if you want the nice symbols, then there is this plugin that is mentioned on our webpage. And so in this case, I can just type \BB and everything will work out. We mentioned this on our webpage. But if you're a bit lazy, then you can, I mean, sometimes I just do this.
Excellent. And the second question, so the right arrow with the exclamation mark means it's a classical mapping or classical function, right?
Yes, so the arrow means that it's a function, and the exclamation mark means that this function is classically known. And the reason we need this is that we also have the capability to capture qubits in functions. And in this case, then you could execute the function only once. So, but this, I think, is a longer discussion that we shouldn't have here. So for the purposes of this talk, just assume that whenever there's an arrow, there's also an exclamation mark in front of it.
I was going to say, if there's only an arrow, I would think of that as a unitary, I suppose, and then you should be able to reverse it, right?
I mean, I think this doesn't really have anything to do with that, because like we can have, so in this case, if there's an exclamation mark arrow, then this is potentially unitary, or maybe I misunderstood you.
Okay. Yeah.
But okay.
That's okay. We can get back to it later.
Okay. Yeah. Let's move on. Okay. So here another thing that's unphysical is if we have this function that tries to apply a conditional measurement, then Silq also gives an error here. And why is this? Well, here we feed in a constant qubit and another qubit. And if the qubit is 1, then we apply a measurement. And of course, or I mean, or at least to me, this is obvious because if C is a qubit, then we don't know classically whether we should apply the measurement or not, which means that we cannot actually realize this physically, because we would sort of have to measure C in order to even know if we should apply the measurement, and that would be an implicit measurement again. So probably what you wanted to write here, or one way to fix this, is to just promise that this C is classical. And now you know classically, oh, C is true, so I apply the measurement, or C is false, so I don't apply the measurement. So that would be one way to fix this.
And on the flip side, so Q is a classical bit here, and I guess I can route the measurement output to some classical bits, which then maybe I can use later to conditionally do something.
Right, so I think you're right here. So this we could, with a decent understanding of what is happening, we could allow this, but Silq's type system currently disallows this. So essentially, like what you could do here is you could essentially observe that the measurement is not even necessary at all, because Q is already classical. So you could remove it, and then of course, if you remove it, then everything is fine. But the Silq's type system isn't smart enough to detect this. Yeah. So, yeah.
So maybe measurement feed forward's not yet part of it.
Yes. Okay. Right. So then another example that we already hinted at before is if we try to do an implicit measurement, then Silq will complain. So let's see, in this example here, we have some collection of qubits that we interpret as an unsigned integer. Let's say, for example, this holds the unsigned integer 7. Now we compute S modulo 2, store it into a new variable. So now S is 7 and T is 1. And if we now return T, then a caller of this function would assume that S is gone, right? Because it was not annotated as const, which means that you would expect as a caller that it's consumed, so you will not access it anymore afterwards. But it's not consumed, it's still around. So Silq tells you that the parameter is not consumed, and it even suggests how to fix this, so you could return it or annotate it as const. So in this case, I would guess that you wanted to annotate it as const. So if you annotate it as const, then the error goes away. And you can say that like now the caller of this function knows if they call this function, then S will still be around and accessible after the call. And so this is an example that I also showed before in a slightly different context. So here, if S is a qubit and we feed it into the Hadamard and call the output T, then if we try to access S again, then we can't do this because S is gone. S was consumed by the Hadamard here, so Silq will tell us that there is this undefined identifier S. And one way to fix this would be to say, well, actually, I actually want to return S, so why not consume a duplicate instead in the Hadamard? So I can create a duplicate of S first, and then feed this into the Hadamard, call the output T, and now the duplicate is consumed, but the original S is still around, so I can actually return both S and T. And if you annotate S as const, then Silq will do this implicitly. So here, S is a qubit, and we annotated it as const. So if we would feed this into the Hadamard without doing anything, then S would be gone. So that's inconsistent with the annotation of const. And instead of throwing an error, which would also be a valid design choice here, we decided that it makes sense to duplicate this implicitly in this case. So here, if S is ket 0 in the beginning, then we would first duplicate this implicitly. So we would get another copy of this ket 0. And then push this through the Hadamard, and Hadamard map 0 to plus. So this would be the final result. S is preserved, and everyone is happy. So these were...
Yeah, quick question on the design here. Like the inputs are typed maybe strictly. The output is unclear, I guess, or...
Oh, right. So the output is just inferred here. So generally speaking, if you know all the inputs, you can infer outputs, and Silq does this. But if you want to be precise, you can explicitly say that the output here is a qubit.
Okay, so you can do some type hinting essentially, or...
Yes. Yes.
I see. And if can the output be mixed, like depending on cases? Does that even make sense?
This, I think it makes sense, or I mean, it depends a bit what you mean by mixed. So one thing that you could mean is this, like it could be a mixture between a qubit and a classical bit. This is totally allowed. Now we get an error because T is not that. But I think what you meant is sort of some conditional typing, where depending on the input, maybe you do other stuff, and then you might return one or the other. I don't think this is implemented currently, but there's no fundamental limit that tells you that you couldn't do it. Just generally speaking, these sort of union types, they tend to complicate the type checking a bit and reduce static safety. So it's not a great design pattern to use them at all, but you could add this to Silq, fundamentally speaking.
Excellent. Thank you.
Sure. Okay, so let's also see a few caveats around uncomputation. So first here, I show stuff that works. So here I just show in practice that my MyOR implementation I showed you before is actually accepted by Silq. And maybe this is surprising because there's actually a ton of implicit uncomputation happening here behind the scenes, because we have this temporary variable not S and not T and the end of both. And all of this is sort of computed and uncomputed behind the scenes. So you can just write your code and everything is nice. This, I think I will skip in the interest of time. But this is an interesting example where uncomputation doesn't work. So here we have S, which is a qubit. And let's say it's in the plus state, so ket 0 plus ket 1. And we feed this through the X gate, the NOT gate. So we again get the plus state, but I rewrote it differently to say that 0 gets moved to 1 and 1 gets moved to 0. Now, if now we would like to forget T, then that's a problem, because after this we have nothing left, right? S was consumed before and T should be forgotten here. And this would mean that overall we would essentially forget this S without ever writing a measurement. So that we shouldn't do this. So, and the reason Silq disallows this is because it says that it cannot synthesize a forget expression for T. So Silq disallows this. But what you could do maybe to fix this as one option is you could have this qubit S. Let's say it's in the plus state again. And now instead of computing the X on S directly, we can compute it on a duplicate. So if S was 0, then T would be 1. And if S was 1, then T would be 0. And so after this, S is still around for the uncomputation. So if we now want to forget T, then T just vanishes here. So everything is good. One thing that cannot be easily fixed is if we try to uncompute a non-Q-free expression. So here, again, we have some qubit S. Let's say it's in state cat1. And then we feed it into the Hadamard, and we actually make sure that S is preserved, right? Just to make sure that it's available for uncomputation. So we feed a duplicate of S into Hadamard. So we preserve S and we get the minus state because 1 maps to minus. If we write this out, then we would get 1, 0, minus 1, 1. And now if we would forget T here, then we get into a very weird situation, because if we remove this T here and remove this T here, then what we get is 1 minus 1 down here, which cancels out. So we get 0, and this has norm 0. And so it's unnormalized, but there's also no hope of normalizing this state. So it's not really clear what should happen in this case semantically. And therefore, Silq disallows this. And it will tell you that, it cannot synthesize a forget expression for T. So that was the last part of my live demo. If there are no more questions specifically to the live demo, I would move back to my presentation and just wrap up like last 5 minutes or so.
Excellent. Thank you. And folks, feel free to post those questions in the chat and we can get back to them as Ben finishes.
Great.
Benjamin.
Great. Okay. Right. So if you want to try Silq out yourself, you can go to this webpage. Installing it is very easy. It's just a VS Code extension. And if you want to get your hands dirty, you could, for example, go to this link. This gives you 2 tasks that you can solve with Silq. And that's a nice way to get started. You could also visit our webpage, and it gives you more of a introduction where you can read up on Silq, and that there's documentation and everything. So there's a lot of resources you can look at if you're curious. And just this side point that I mentioned before, Silq doesn't come with a compiler currently, but in this uncomp project, we synthesized uncomputation gates in Qiskit specifically because, sadly to say, Qiskit is still much more widely used than Silq. So we wanted to get these ideas of synthesizing automatic uncomputation also available to the Silq community. And in this project, you just have to annotate your qubits as being temporary, and then the synthesis procedure will automatically generate uncomputation. And this doesn't only result in nicer code, which in this case was 90% shorter, but it also reduces the number of gates and number of qubits compared to stuff that was already natively implemented in Qiskit. And we believe that the reason for this is that if you automate this process of introducing uncomputation, everything just gets a lot more consistent. So you can consistently apply optimizations, you can more consistently handle the allocation of qubits, and overall this then results in more efficient circuits. So if you're concerned that Silq being more high level means that it's less efficient, then I think our preliminary results suggest that this is not the case, in the contrary. And just to wrap up, I want to very quickly broaden the view and explain that from a bird's eye perspective, this Silq is just an application of classical programming language research to quantum computing research. So in this case, we have used some, partially these ideas were already all around, like this const idea, for example, is not totally from outer space. Similar concepts exist in Rust, for example. And applying these concepts to the problem of designing a nice quantum language, I think was quite beneficial in this case. But there's also a lot more that happens in the programming language research. So programming language has a lot of programming language research has done a lot of progress on compilation, static analysis, verification, or even synthesis. And I believe that these solutions could match quite well with some of the open tasks in quantum computing research, such as circuit generation or circuit optimization or error correction, maybe more. So I'm hoping to see a lot more of these types of works that connect classical knowledge from programming language research and apply them to quantum computing research. With this, I would like to thank you a lot for the invitation and for all the questions and for your attention. And I'm happy to take questions if there are any.
Thank you, Benjamin. This is really nice. Maybe first question from Nazo. Is there any literature to this, or what's the point of reference for Silq?
Right. So I assume you're talking about Silq specifically. In this case, if you want to just so there's a few points of attack, right? Like you can go the practical pathway and like follow the installation and just solve the task. Alternatively, you could visit our webpage and there's a lot more discussion there. Or you could read our paper, which is linked on the webpage that discusses Silq. So depending on if you're, I would say these are ordered from most practical to most theoretical. So depending on your preference, anything can make sense.
Great. Well, one of the questions, and maybe you just addressed this in your last, was does Silq export to QASM?
Right. It's a good question, and I think eventually it should. Currently, it doesn't because, as I said, Silq doesn't have a compiler currently. I would say that this is not a fundamental restriction, but it's a very labor-intensive task to write a compiler, especially because Silq is so high level and we're a team of maybe 3, 4, or 5 researchers, depending on how you count. So this is a major undertaking, writing a compiler. But fundamentally, I don't think it's an issue.
And how does one debug or see the outputs, or how does one sort of use Silq now to compare to what would happen?
That's a good question. So let's see. I can actually, I think I can show you like one example. So here, this would be one example of this getting your hands dirty exercise. Here we see an implementation of Grover, and you're supposed to write some dummy oracle, which I will not show because this would give away the solution. But if I press F5 now, then this brings up the simulator, and it will show that running this program actually returns the value 19. So you can, of course, use a type system, which is already quite nice. A lot of errors will be caught there. But if you actually want to execute Silq using its simulator, then this is also built into the VS Code extension.
I see. Very nice. Maybe kind of a high-level question. So it seems like the basic tenet on which this language is developed is really working on the computational basis binary strings, this kind of programming framework where you're really thinking about what's going computation on the basis strings. This is maybe a perspective question. Do you think for quantum computers and quantum computing, that's the way to focus and the way to think about it? Or are there other frameworks or ways to think of processing and encoding the data that should be thought about or considered? Is this rich enough, essentially, of an even setup to think about?
Right, this is a great question, and I think the answer really depends on the domain. So if you're talking about Grover or some applications from quantum finance or stuff like this, then typically you will have a big classical part in there, maybe encoded as a quantum oracle. And in these cases, Silq is very beneficial because if you don't have Silq, you will be totally lost in all of this uncomputation business, and it's very hard to get this right. So in this case, I think Silq is absolutely the way to go, or something like Silq, right? Like, I mean, I see Silq sort of as a collection of ideas that could be incorporated into other languages as well. If you're talking about an application like quantum chemistry, then it's a bit less clear, because there's not so much classical computation going on. there's still stuff like some sequences of controlled X gates, and I think there are some possible applications there. But I think the benefit, let's say, is definitely less for quantum chemistry than, say, for some search problem you want to address with Grover. Does this answer your question?
Yeah, I think that does give me. Does Silq have a notion, or is it useful to, let's maybe even beyond Silq, do you think it would be useful to think about changing the computational basis? In a lot of these algorithms, you're sometimes going from a Z basis to an X or some other. Is that a notion that would be useful in a language like this to be able to essentially change and work in different bases? How do you think about that?
I'm not sure if I interpret your question correctly, but it may connect to something we have been thinking about. So maybe what you're saying is, Silq is very focused on the computational basis states, but maybe you could generalize it such that it also makes sense in the Y basis or the set or like X basis or something like this. Is this what you're saying?
Yeah, exactly. Because essentially, in a lot of these algorithms, you do a Hadamard on all the qubits, yes, which is changing from one basis to another basis. So in that basis, you now have some very well-defined string as opposed to a superposition across. So essentially, something that looks like it covers the whole support in one basis is very localized in another basis. And sometimes that's useful to think about, but
I think so. So part of the answer is that even if you have Hadamars in there, that doesn't necessarily trip up Silq, right? So in my example, for example, there is a Hadamar in the very beginning and in the very end of the circuit. So that's not necessarily a problem, but still, I think your question makes sense. And we have been thinking if sort of this Q-free concept, for example, could be generalized to a Q-full concept, right? That is sort of the analogon in the X spaces or something. But so far, this is just an idea. Like I think there could be something there, but I haven't investigated further. So that's interesting. Food for thought, I would say.
Interesting, right? This is so broad, so I'm going to have very broad and many questions. How about, have you thought more about, or are there kind of examples of things like the swap test or the Hadamard test in here? These kind of primitives that you see that involve unitaries and measurements with ancillas, and there's usually multiple versions of those. There's destructive versions and there's kind of more unitary versions. I'm not sure it's a well-formulated question, but
Are you maybe referring to a potential problem that says if I implement some circuit, if I implement some unitary gate, but I have a specific trick that allows me to leverage a measurement, then this function will not be M-free, even though conceptually it is. And now we get into a problem with it. Is this the type of thing you're interested in?
I think so, yeah. And I guess phase estimation is maybe another example to think about. You've probably thought about where you can use many ancillas, or you can use measurements, with one ancilla, and like you said, sometimes.
Yeah. So I think so. First of all, I would say like this example where you implement a gate, maybe using a measurement, even though conceptually the gate is not M-free. This, I think currently we haven't implemented this, but it's not really a fundamental problem because you could just fix this by a type coercion. So you can just say, like, even though this function doesn't look M-free, it conceptually is M-free, and therefore I know what I'm doing, just allow me to annotate this as M-free. So like in terms of the type system, this is not necessarily a problem. I think for the second part of your question, you're referring to the fact that just uncomputation itself may not be the only potential you can leverage, right? So for uncomputation, for example, you can decide if you want to uncompute early or lazily, and this will give you different patterns of the usage of your qubits, and everything could be interesting. And that's a lot of food for thought when you develop the compiler. And similar stuff could also appear if you do quantum phase estimation. And I think ultimately you're right that there's more potential than just the potential that Silq abstracts away. I mean, like one answer would be that Silq is probably not the end of the road here, right? So Silq shows you how you can have a very nice framework for these sort of uncomputations and temporary variables. But I assume that similar progress can be made for other tasks like quantum phase estimation. But I don't know yet how this would look like.
Okay, great. Thank you. Folks, feel free to post any final questions. We're 15 plus minutes over. So Benjamin, maybe I'd like to turn this over to you if you'd like to share any final words with us here.
Of course. So one question I just noticed in the chat is the advice for beginners. And I think what's very nice is Scott Aronson has some lecture that we also cite on our webpage. I think it's even stated as like if you want to get started on quantum computation. So if you're curious, just browse our webpage and there are some great resources there. That's not even from us, right? It's just like Aronson has produced some great work. So I can only recommend this. And other than this, I mean, thanks again a lot for the invitation. Happy to present here. Thanks for the honor and hope to see you around.
Excellent. Thank you very much. Yeah, those are nice notes. I'll mention that they're definitely more digestible for folks coming from a CS background, and that's a really good fit. And for a broader background, I can suggest the usual Qiskit textbook and tutorials or some of the other resources. Thanks for posting, and I think we just posted the Silq website for reference, so you guys can see that.
Perfect. Thanks.
Thank you, Benjamin, for the very nice talk. I think it's a really interesting question, and it looks like some major progress. And folks, thank you for tuning in. This talk will stay recorded, so you can go back and watch it. But to know what's coming up and to tune in live and ask questions and discuss amongst each other and the speakers and myself, hit that subscribe button on the Qiskit YouTube channel. And with that, we will see you next Friday at noon Eastern Time.